Hey, Year 12s, let's recap. Let's see what we've learnt. Last lesson on Monday. What did we learn again? Aaron? Oh, that's right. You were away, mostly away from that lesson. Did you get the revision?
Not yet.
What did we learn last lesson, Steph? Exponential graphs. What did we learn about exponential graphs, Ian? Gradient. No, we didn't learn about gradient. That's derivatives. Trent, what did we learn about the graph? There were two properties. Name me one.
They flip place when you change numbers pertaining to the x or pertaining to the y.
Fantastic. That's called transformations, but I'm talking about properties. Exponential graphs. They all have two properties. What are the two main ones, Athena? Horizontal asymptote. What is the equation again, Richie? Y equals 0, not x equals 0. Y equals 0 is your asymptote, and then one more property. So you got a horizontal asymptote because you can always keep halving, or you can always keep doubling. So it goes infinitely large and infinitely small. That's your exponential graph. What's the other property, Dodger? Y-intercept is 1. Why is the reason? What's the reason for y-intercept being 1, Drew? Very good. Excellent. When x equals 0, anything to the power of 0 is 1. So we know for a basic graph without any translations, it will make sure that you have an intercept at 1. So this is what your graphs will look like. Intercept at 1, asymptote y equals 0. One more thing. Just before the end of that session, I also mentioned one more property that I said most students forget, and it only came up in one of a year's exam as 1 mark question. I said, what are the restrictions of an exponential curve, Judd? Not x base is bigger than 1. Okay, you can't have it less than 1 if it's, well, you can, like if it's half, you're technically changing it to the inverse or the reciprocal, yeah? But it can't be 0 and it can't be 1, otherwise it's a constant. What happens when it's a negative though? So if you have, let's say, -2 to the power of x, what's the problem with that? Yeah, because the powers would change it. If it's an even power, it's all positive. If it's a negative power, it drops down. So you get an exponential jagged sort of dots going around. Yeah? But there you go. So that's your 3 properties there. A has to be greater than 1. These are my graphs now. That's 2 to the power of x. This is 3 to the power of x. Now, before I sketch it, what can you say about 3 to the power of x? If I increase the base, what should the graph look like? What can you tell? If this is 2 to the power of x, how does 3 to the power of x look relative to 2 to the power of x? What's the difference? It is steeper. Good. So past 0, 1, it is steeper because you're tripling it. Okay, so for every 3, it's like 3 to the power 1 is 3, 3 to the power 2 is 9. So you're tripling it. Triple 9 is 27, triple 27 is 81. So the rate of increase is much higher. But then what happens in the negative region? It's smaller because now you're thirding it. You're making it much smaller. You're showing it by 3 rather than showing it by 2. So if you've got a pie, you want to cut in 2s or you want to cut in 3s. The more you cut them, the smaller they get. So on the negative side, it would be smaller than the blue line. On the positive side, it should be larger or steeper than the blue line. So this is what it should look like. Okay? And if I change it to 10 to the power of x, you can then expect it should be very steep. Much steeper than the red, but also smaller than the red on the left-hand side or on the negative side. Yes, Trent?
What are the exponential relation look like?
Relation?
It's like with the exponential equal half. So square it to make it half.
Square it? You mean like give me an example. 2 to the power of half. Ah. Which is the same thing as root of 2. Which is 1 point something. Oh, no. Oh, I see what you're trying to say. Oh, I see. So, oh, do you say that? So it goes back to constant functions. When you start putting it like this now, right? You're saying that the square root can take positive or negative numbers, right? And what that tells me is that the y values can be positive or negative, meaning that you can have a negative down here. But that now changes the domain. So, or the range, sorry, the range of the function. So, yes, it might be a relation, but then that's now talking about only for every second one, because it's only when you square root, so 4th root, 6th root, 8th root. So I don't know what kind of relation that is, and whatever relation that is, I don't know if that's an exponential sort of relation. Yeah, so it is a relation, you're right, but whether that's exponential, I don't know if that's what we call exponential. By definition, we'll be talking about this is my exponential curves. Anything that's in that particular shape, we call that exponential. Anything that looks like a U, we call that quadratic. Yeah, and then anything after that, we call them even functions. Yeah, but there you go. That's your exercise 5A. 5B, pretty simple. We're going to transformations. Now, let's have a look at your transformation skills now. So 5B, questions, can you read the transformations now without doing what you did in chapter 3 where you have to rearrange things? Can you tell, is it moving left? Is it moving right? Is there a reflection? Is there a dilation? That's what I want you to be able to do. So I'm going to give you a couple of minutes to have a look at this. I want you to write the notes for A, B, C, D. I'm going to call out your name and you're going to tell me the transformations for each one. You can either do what you did in chapter 3 or you can just look at the equation and pick it up. That's the ideal. I want you to be able to look at it and then just tell me, do I have a reflection? And if it's a reflection, in where, which axes? Use the correct terminology, use the correct language for it. Translation is always the easiest one to figure out. It's the dilation that you got to make sure you don't do wrong. Let's go. Should give you 2 minutes. There we go, 2 minutes.
This is from the black one, or but and then it's this way. Dilation.
The answers could be slightly different depending on your order of sequence. One more minute. And when you're writing your sequence, do it Dr. T. Dilation, reflection, then translation. Normally it doesn't. Yeah, dilation and reflection shouldn't. It's just conventionally we do dilation, reflection. All right, here we go. Let's go through the answers. A. Aaron, name me one transformation for A. In the x-axis. Fantastic. The negative of it, I'm going to do a highlight, actually blue. Negative here is a reflection in your y-axis. So reflect in the y-axis because it affects your y values there, not your x. So you can see where the negatives are. So it's reflection in your x-axis. Sorry? Yeah. Didn't I say that? No, I said it's reflecting your y values. Okay, sorry. Oh, did I say y-axis as well? Oh, my bad. X-axis, but affecting your y values. Okay, because it's affecting your y values, it's reflecting in your x-axis. So your shape, instead of looking like this, it should be like that now. Okay, so that's what we know. Give me another transformation, Basil. Fantastic. From? In the y-axis, is that correct? Not in the y-axis. In the y-axis implies that you're stretching it this way because that's along the y-axis. What you want to say is from the y-axis. Because you're dealing with the x's, it should be pulling this way. So that's moving away from your y-axis. Trent. You are getting thinner, but the language that you use, you're actually stretching this way, but technically it's compression. Because it's a third. It's times by a third, so it's a horizontal dilation, so a horizontal stretch. So the language that you use, you would either say it's 1/3 in the x direction, because it's on the x-axis, you're doing 1/3 of it, or you're saying it's moving away from the y-axis. It's not moving. It's not moving. It's getting. Is it a horizontal stretch or is it a vertical stretch? That's all it is. So it's more of a language. So when you describe it, yes, you're right. It is a dilation of factor 1/3. So it's a dilate factor 1/3. Now you can either say it's from the y-axis because you're moving away from the y-axis, so it's getting stretched out, okay, or stretched in, compressed, okay, or you can say in direction of the x-axis. Either way is correct, okay? And in the exam, they'll use either one of those two. It's either from or in the direction of. But you don't say in the direction of y, because that now implies that you're getting stretched vertically. Okay? So that's your 3. And then finally, -2. What does that tell me, Jun? What does the minus tell me? Down 2. Fantastic. Okay, so if you were to picture this graph already, yes, you're right. Dilation of factor 3 means we squish it horizontally, so I squish it horizontally so it should get thinner. That's why it kind of looks like you're stretching in the y-axis. So it gets compressed and then down by 2, so the asymptote instead of being at 0 now goes down to -2. Okay, so I know it's gone down -2 means my y-intercept changes, and from this I can also tell there's no x-intercepts as well, so there's no point solving for it. Okay, and that's what exercise 5B is about. You need to read the transformation, picture what the graph is, and then sketch it. Yeah? All right, so we got A down. Let's have a look at the next one. Give me a transformation for B. Can I please have Liam? Fantastic. Reflecting the x-axis again, so reflecting the x. And then finally, I've got this 3x plus 1, which could be a bit tricky here. Give me one transformation here. Can I please have Athena? Good. Dilation of factor 1/3. Dilation of factor 1/3 from the y. Fantastic. Because you're affecting your x value, so it's moving away from the y, or it's in the direction of the x, whichever you want to call it, right? So moving from the y. And what else? What's the last one? Can I please have Ben? What am I missing?
Translation of back to the
It is left, don't say factor. Factor is only for times or divide, and you would say unit. So translation of 1/3 unit to the left or in the direction of the negative x direction. Negative x direction, okay? But in that case, yes, you're right, it is also a third. So remember, just be careful. These ones here, Dr. T comes in. So if you remember, this is the same thing as saying your transformation is 3x dash plus 1, and you want to know what the x dash is, the transformation. So you have to rearrange everything. You get 3x dash equals x minus 1, and then you divide everything by 3. So you can see it's x 1/3 dilation, and then it's minus 1/3. That's why you know it's left by 1/3 and dilation of factor 1/3. Okay, and it's affecting your x values. Next one, C. Give me one transformation. Can I please have Anna? Good. Dilation of factor 2. Whoops. Factor 2 from the x-axis because you're now affecting your y value, so it's moving away from the x, or you can say it's in the direction of the y, whichever one you want to choose. Give me another transformation. Can I please have, let's go with Michael. Fantastic. That x on 2 there tells me it's a dilation of factor 2 from the y-axis because it's affecting my x values. So it's from, moving away from. And the last transformation, what do I have, Daja? Fantastic, that is correct. Translation of 2 units to the right. So translation 2 units right. And again, same thing. If you're, the hardest one is your horizontal, anything to do with the x's. That's the one that's confusing. I always get you to practice instead of writing it out. That's your new x. You want to find the x dash. And so you rearrange everything and you can see it's x dash on 2 equals x plus 1 and then times 2 on both sides. So your transformation is obvious. And it's 2 times the original, so dilation of factor 2 from the y-axis, and it's moving to the right by 2. That's how you can tell. Okay? So just learning how to use chapter 3 again. Last one, D, the tricky one here. Well, not tricky, it's just more transformations there. D, name me one transformation, please, Alessia. Fantastic. This is a reflection in the x-axis. So reflect in the x-axis. What else do I have? Can I please have, let's go Richie.
Y-axis.
Reflection the y-axis, good. Reflect in y. Mazen? Oh, not 1 unit. Oh, wait. It depends on how you describe it first. It is 1 unit. Well, overall, it's to the... Yeah, you're right. It's to the right. Yeah. Okay. And again, same thing. Just in case you forget or you find it troublesome, just write it out. Rearrange it to find x dash, and you can see it's negative 4 x dash equals to x minus 4. Divide both sides, and you get negative x dash on 4 plus 1. Sorry. There you go. Okay, so you can tell that you can read what Mazen said. It's moving to the right by 1. And I'm also now missing just the dilation, which is dilation of factor 1/4 from the y-axis. So I'm affecting my x values. Okay, how's that feel? Pretty good? Okay, that's exercise 5B, but it's also a revision of chapter 3. Okay, so the better your chapter 3 is, the easier it is to do 5A and 5B. You're just sketching.
Wait, this is 5B.
This is 5B. I know. I made a mistake. Yeah. It's all right. It's all good. So here we go. I'm just going to move forward. That's 5B. So if you have a look at it, pretty straightforward what I just said there, but I want you to sketch it now and set the range. So that's what I'm saying. If you can picture each one, if you can read each one, you should be able to read the range, and you can tell me the properties. That's the aim. Okay, so you should be able to read all these now. Down by 2, left by 1, dilation of factor 3 from your x-axis. Okay, so those are the skills I want you to be able to do for 5B. Now, 5C. These are the laws that you have learnt back in year 9, 7, and 8. Index laws. I normally, if I had you in junior classes, I would have taught you why each one of these are, but by now you're just going to have to memorize them now if you don't know them. Okay? Now, the one that most students forget is not here. Anyone know which one I'm missing? There's one more. Number 8, yes. There's a law number 8. What was that one again? Most students forget this one. Not the log one. It's all exponential right now. What am I missing? Oh, let's write it again. 8 to the half is the same thing as? square root of a. So that means if I have a to the 2/3, this is the same as? Good. Okay, and that rule was a to the mn is equal to a to the power of m square root n, root n. Okay, and it makes sense because this is the nth root. That's how many nth roots you have. M is the power. Okay, number 8 is there. Yes, it does. That's a very good question. I want you to listen for this one right now. Steph asks, does it matter in this question here whether you square it or you cube root it first? Now, it doesn't matter in terms of the algebra, but it does matter when it comes to functions. What was the reasoning again? I explained this one when we first started chapter 1. Why does it matter? What was the issue? What was the issue again? Yes, it was composite functions, but what's someone define to me and prove to me why it mattered?
There is some restrictions on
Fantastic. Now, in this example here, it doesn't matter. Why doesn't this example matter? When does it matter? When will it matter that it is an issue? Right now, I know this one wouldn't have an issue. 2/3 won't have an issue. It will take all real numbers. Which one won't? Aaron?
It's difficult the other way around, because then you could have a negative, like when you cube it, you can have a negative number when you square it.
Perfect. Exactly that. So, in this particular question, when you do the algebra, it really doesn't matter whether you square it and then cube root it, or you cube root it and then square it, it will be the same thing. Your problem comes when you start square rooting. Any nth root that is even, so 4th root, 6th root, 8th root, that'll become an issue. So if you did switch it around, you had 3/2, it does matter whether it's a cube and then 4th root it, or whether it's 4th root and then cube it. Because if you 4th root it, that means you can't have any negative values, and then you cube it, so it's always going to be positive. Whereas if you cube it, you can have negatives, and then you 4th root it, yeah? And that becomes a problem too, yeah? So that's why, yes, you can have the graph, but it can only have one function. In that case, you would have to 4th root it, then cube it, but it's impossible to cube it and then 4th root it, okay? So that's the only thing that you've got to pay attention to with those, what are they called again? Rational powers. Okay. All right, so you got these laws here. When you times, you add the powers. When you divide, you subtract the powers. When you times them, you got your groups, the m times n, and you got 0 to the power 0 is 1. These are your basic skills. Now, 5C, the first few questions is just working on your algebra again. So working on your exponentials. If you're good at that, you don't have to do questions like this. Like, to me, that's just tedious because you already know how to do it. You're just spending a lot of time working on these. So like when I do this question, for me, I see 3rd root is the same thing as saying all to the power of a 3rd. That's 8x to the power 6, t 15, 27x 12, t negative 2. I then use the exponential rule where if you have brackets, you can multiply the powers. Yeah? And that makes it easier because if you do it that way, it's really just saying 3rd root of 8. 3rd root of 6 becomes x2, 3rd root of 15 becomes 5, and then 27 third, and then x 12 divided by 3, which is 4, and then t negative 2 on 3. So that's much easier to work with. After that, 3rd root of 8, 3rd root of 27 is easy. You know, 3rd root of 8, which is 2, 3. Now you got x squared divided by x to the power 4. What's x to the power 2 divided by x to the power 4? X to the power of negative 2. Because when you're dividing, you're subtracting the power. So here you got 2 take away 4 is a negative 2. So it's x negative 2. And then you got t to the power 5 divided by t to the power of negative 2/3. So you subtract again 5, take away negative 2/3, really becomes 5 plus 2/3. And what's 5 plus 2/3? 17 on 3. Yeah? So this is now t 17 on 3. So if you put it all together, you got 2t 17 on 3, 3x squared. Okay, so I've used all the skills there. I've times them, I've divided them, I've expanded, and over here I've changed the negatives to the bottom powers. Yeah? So that's what I'm saying. You're using all those 8 laws, but you find your way to do it. I like to expand like this. This is how I would do it. You can find many other ways. You could simplify it first, and then do a third. It's up to you how you want to do it. But as long as you can learn how to simplify, that's what the first few questions of 5A is, 5C. Okay? What about the next one? You guys have a go with the next one. I want you to simplify this. Comes up every now and then, and kids are like, I don't know how to do it. Give it a go. It's a pretty nice simplification. I want you to go with this one. And then I'll go through one where it's usually on the exam, and note that question is usually on the SAC, usually on the exam. It's worthwhile doing in the next slide. So these ones are just, you'll never get these in the exam. You just don't get these. Yeah? I think it's a waste of time, that's why. Yeah. It's tedious. So you might get it in like, no, you won't even get it. I don't think of a way. Nah. How would you do x squared plus y squared divided by x negative 2 plus y negative 2? How do you simplify this? This is really good because it also shows misconceptions when you were in year 7. Things that you learn like fractions, things that a lot of students just cancel things out without knowing why it cancels out. And this is where the errors come in. So let's have a look at your year 7 fractions. Sorry? Your revision. Or catch up. Or move on to 5C, wherever you're up to. Yeah. I reckon at my pace I might even finish chapter 5 before your SAC, which is good. I'll be on track. You caught up. Alright, here we go. Let's look at our answers. No? You don't have to look up. First thing, negative powers. You can use one of the laws you've learnt. If it's a negative power, you can rewrite it as 1 over x squared. And that's the first thing I do. So you have 1 over x squared plus 1 over y squared. Now the issue here is that a lot of students think you can just go cross, cross. It doesn't happen like that. You can't just cross things because there's top and bottom. It's usually, the only reason why you can cancel them out is because you're dividing them and it goes in nicely. So it's a factor. So x squared divided by x squared, they both have factors of x squared. That's why it becomes 1. Okay? In our case here, it is not the same. This is x squared divided by 1 over x squared. But remember there's a plus, so this goes together. They're not separate entities. If it was times, yes, you can treat them as separate entities, but when it's addition, they come as a whole. So what you have to do now is group these two to make yourself, you have one whole denominator, because right now you've got 2 terms in the denominator. So what I'm going to do here is I'm going to do cross multiplication to put them together. This is what I get. I got x squared plus y squared over y squared plus x squared over x squared times y squared. Have I gone too fast? Okay, all right. Here we go. So numerator is still the same, right? What I wanted to work out was what was 1 over x squared plus 1 over y squared. True? Now, in year 7, we learnt a method called cross multiplication, or you can think of it as the only way for you to add and subtract is you need the same denominator. Right now, one has an x squared, the other one has y squared. So what I can do is I can say times this by y squared, times this by y squared. So the denominator is x squared, y squared. Then I can do the same for this one. I can say times that by x squared, times this by x squared. Why? Because now this becomes y squared over x squared, y squared, plus x squared over x squared, y squared. Can you see what I did there? See, all I did was I multiplied y squared over y squared. That technically means 1. I haven't changed this fraction. It's an equivalent fraction. This is also an equivalent fraction, x squared over x squared. Well, by doing this, I will get x squared and y squared for both of them. Now I can add them. So I can add fractions now. I can say, yep, denominators are the same. How many of these x squared, y squared fractions do I have? I've got y squared plus x squared. So if I combine those two together, this now gives me y squared plus x squared all over x squared, y squared, which is what I was writing underneath here. Okay, so I did the cross method here and I simplified it over here. So that's my numerator. My denominator is this fraction. So if you write it down, this is my fraction. I've got y squared plus x squared over x squared, y squared. Well, how do we feel? Does that make sense so far? Yeah? Okay, now, this is where a lot of students find it difficult when they're doing this question. You see in the exams, you know, they'll do, all right, let's just cross, cross, cross. You get 1. Yeah, and you probably could do that, but you have to show the algebra to this, and it shows how well you understand your algebra and your fractions. Yeah? So right here, a lot of the times I try to describe students, I say, that's your numerator. This means divide. So write it down. That, divide, that. That's your fraction. So if you write it out, it's very easy. So once you write it out, it looks like this. You've got x squared plus y squared. You're saying divide. You got y squared plus x squared over x squared, y squared. Now remember, when you're dividing fractions back in primary school, what do you have to do again? You do the reciprocal. Do the reciprocal, now you have x squared plus y squared. Now that is one entity times x squared, y squared all over x squared plus y squared. Now you can see, when you're timesing them, this is multiplied to 1, it goes down the denominator. These two, yes, you can cross simplify. This entity divided by this entity is 1, because they go in one whole. They both have the same factor. Yeah? So these will cancel out, and your final answer will just be x squared, y squared. How was that? It's good? Yeah, so if you felt that there was some trouble, I do recommend you doing questions like that. There's a few in your exercise 5C, only because that's what the examiners will be doing. So that kind of level is what they expect you to be able to do, to simplify it down to x squared, y squared. What you see over here, very unlikely to get. That one over there, yes. See, that one's nicer. That's a possibility that you can get, but not or something like this. Okay, so work on that skill if you're finding your fractions not too, sort of, you need a bit of a brush up on that with a lot of pronumerals. Work on that one. Okay. Otherwise, let's go to what you will see in the exam. Okay, not these ones, but we're working on to that. Let's do this one. This is we're going back to what, year 9, year 10? Exponential equations. How do I do this one again? Without using log. Without using log. We apparently haven't learnt log yet. So, how do we do this one? That's year 9, 10, no logs. Trent.
Just knowing that 9 squared, 9 squared, no other way.
Yeah. At this point, the only way to solve exponential equations without log is by solving it by equating them, meaning that the quantity for both sides is exactly the same. If you know that they both have the same quantities, then everything has to be the same. So over here, you know this is a base 9 to the power of 2x minus 1, but you also know that 81 can write as 9 squared. Now that you have the same bases, and you're saying that these two equal to each other, what you can say is that means the powers have to equal to each other. Okay, so if the powers are equal to each other, then you can say, therefore, 2x minus 1 has to equal to 2, and then suddenly you got something you can solve. That becomes 2x equals to 2 plus 1, 2x equals 3, x equals 2/3. Okay? So that's what we would have done in year 9 and 10. We're working on this. Now let's move to the next one. Same goals. How do you do the next one? Same goals. You want to get the same base. I've got a base 5 over here. The goal is to make the right-hand side a base 5. How do I do that? What do I do? Yes, Mazen.
5 equals 5
Yes, you can do that. You got 5 to the negative x is 1 over 5x. That is true. You can do it like this. We're getting close. There's a lot of ways to do this, by the way. Sorry? Did I write 2 and 3? Oh, sorry. Rookie mistake. Thank you. What do you do from here? Yeah, you know that 25 is the same thing as 5 squared. Now, notice, they both have the same quantities. It's 1, 1 equals, they're both the same. Both base 5, so that means the power has to be the same if it's equal. It's because you wrote equals here, or they wrote equals, that means you can say both of them have to be the same. So in that case there, if the powers have to be the same, oops, x has to equal to 2. Okay? Alternatively, you could have changed the 1 on 25 as 1 on 5 squared, which is the same thing as writing 5 to the negative 2. And that would have worked as well. So you would have had 5 to the negative x is equivalent to 5 negative 2. Therefore, negative x equals negative 2. Therefore, x equals 2. So they both work as well. Okay? But you can see the skill there is you're using all the exponential laws and you're trying to solve it by making them equal to each other. Now, it gets trickier when you start doing questions similar to, not that one, actually, I'll do the next one, the ones after. I want you to try this one now. Try C. Have a go at C. Using all the laws, remember your aim is to get the bases the same. Get the same bases, then you're good. Where's my eraser? Why isn't it coming off? I don't know why. Okay. C. How do we do C? So out of all of chapter 5, I really think 5C is the beginning. Remember I said chapter 5, chapter 6, your goals are to learn how to do your algebra. Sketching by now you should be good. Transformation, sketching, all of that should be good. It's your algebra and exponentials that we're revising for chapter 5. And that'll be for your next SAC. So preparation for next SAC, you should practice 5C. That's what you want to do. Where did I write it? It shouldn't be. I think you have 2 in term 3. I think. I'm pretty sure it was August something. So we have time to learn chapter 5, chapter 6, chapter 7, chapter 11. Four chapters. That will be exponential logs, circular functions, integration, and revision of chapter 1 again. That's what chapter 7 is. And that's 2/3 of the year for you by that time. By August, you only got a few months left before your exam, so yeah. 75% of your stuff is there. Alright. C. What's my first step? What do you have to do? What did you do? Can I please have, let's go with Rose. What'd you do? Good. Fantastic. Excellent. Remember, when you're multiplying the exponentials, if the base is the same, you can add the powers. That's law number 1. So here we can say it's 3 to the power of 2x plus 2x minus 1. If you're doing these in the exercise or the exam, be careful if it was a division. Because if that was divide, a lot of students will write a minus here and then write 2x minus 1. What's the issue by doing that already? You're meant to have, if you write a minus here, you got to remember, it's not just minusing 2x, it's also minusing the negative 1. 2 negatives become positive. That's where the errors come in. Okay? So, because it's plus, you don't have to worry about that. That's equal to, now you want a base 3, 27. How do I change that to a base 3? Verity. Good, 3 to the power 3. So now I can say, this is the same thing as writing 3 to the power 4x minus 1. That's equal to 3 to the power 3. Now that the bases are the same, that means the powers have to be the same if they're equal. Therefore, you have 4x minus 1 equals to 3. And then linear algebra. So what that becomes 4, x equals 1. There you go. Simple and easy. 5C. Now, let's move to... Don't worry about that. You can keep doing that. This is the one I want you to work with. Here we go. Have a think. These are your typical questions for your exam. So, if I want to find these kind of questions, it's either the log type or it's an exponential type. Usually 2 to 3 marks every time in exam 1. Okay, every year there's going to be one form of that, and I promise you will be there. Okay, so these are the questions you'll have, and it is in your exercise as well. It's 5C, the last few questions, which are on the next slide. This is what they want to test. This is what they want to work, because it works with your quadratics, and it works with your sort of exponential skills there. Most students find that a bit tricky, but it is easy once you recognize it. How do you do this one? I made it easier by putting a bracket there.
This is the 2A thing. Yeah, it's not one.
What's the 2AA?
The one where you replace the 5 parameters with like A or something.
Fantastic. Is that what you were going to say?
Yeah, I just want to. Yes,
Yeah.
it becomes like 2A.
Absolutely. So the trick here is, unlike the other one, you have to try to find the same base. This one, you're meant to recognize 5 to the power of 2x is the same thing as writing 5 to the x all squared. And then you got minus 10 times 5 to the x plus 25. Now what you can see is that the only commonality here is you've got 5 to the x. Now to make your life easier, we can change 5 to the x to let that equal to a. We can say, let's make our problem easier by saying let a equal to 5 to the x. Because if I do that, I can replace this to be a squared minus 10 times a plus 25 equals 0. Now if you have a look at that, that's just your quadratic. See, if I just rub off the brackets and rub off the times, it's a squared minus 10a plus 25. That you can solve. That's something that you're familiar with, right? So let's work this out. We have to factorize because it's already equal to 0. Find me the factors. What would they be? Minus 5. Minus 5. Good. So this works out to be a equals to 5 if you use null factor law. Why am I not done? You have to find x. It wasn't a was a made up variable. You made it up to make it easy. So now you know that a equals 5. You got 5 to the x, therefore x has to equal to 1. Because this is 5 to the power 1. If the bases are the same, the powers have to be the same. So that's why you know x equals 1. Now in your exam, the reason why this is an exam question, not because I made this one up so it's easy. Usually you'll have 2 answers here. You have 2 different answers, you get 2 different A's, and then you get one where it works, and one doesn't. You have to justify it. So every time you get a 3-mark question, there has to be a justification somewhere. You have to prove that it's undefined. In this case, x equals 1. But there are other cases where when they do it, it's a 3-mark question, they want you to justify it. They want you to say it can't be because e to the power of something can't be negative or can't be 0. Okay? Here you go, you try this one now. I did the other one, you did this one now. Let's go. Try the same drill, same idea. Try to pick out the quadratic. Rearrange it to get your quadratic, and then that's it. That's your chapter 5, exercise 5B, 5C. So transformations in algebra, exponential. When we get to logs, you'll find there will be another similar one to this as well. You get a quadratic. And it's always going to be either one of these two. It's either the exponential or log. They come up every year.
But it's correct. Right.
Sorry?
But it's correct.
You have to test that.
You have to test it.
Well, as in test by looking at the original equation. I'm pretty sure it should.
Some of that is, you have to do that. So it shows each.
You don't have to sub. It's just you. At the end of it, you just write whether the answer is 2 or 1. Yeah. If it's undefined, then you have to say undefined since whatever it is. But if it's not undefined, then you just write your answer. That's why the third mark's always a justification, meaning that if something isn't there, you can't just ignore it without saying why it's not there. But if you leave it there without saying anything, then they assume that you can have them. So if you don't write anything, it's always assumed that's what you can have. Alrighty, here we go. Let's look at our answers. So, key thing, this is 2 to the power of x. Your aim is to make something with a 2 to the power of x as well. Hopefully you picked up 4. 4 is the same thing as writing 2 squared to the power of x there. This is minus 15 times 2 to the power of x. And then a minus 16 on both sides. I get 0. So this is getting your quadratic equation. And you remember, this is the same thing as writing 2 to the power of x squared. Okay, because using law number 3, it's the same. 2 times x or x times 2 is the same thing. So minus 15, 2 to the power of x minus 16 equals 0. Now what you can say is let a equal 2 to the power of x, and it makes it look easier. A squared minus 15a minus 16 equals 0. Factorize. A 16 is like, what is that? Maybe 16 and 1? Yeah. Therefore, A equals to negative 1 or A equals to 16. Now, if you sub it back in, you have negative 1 equals to 2 to the power of x or 16 equals to 2 to the power of x. Now in this case here, you can write 16 as 2 to the power of 4. Therefore, x has to equal to 4. What about negative 1? Undefined. Okay, remember your exponential graph. If I asked you to sketch 2 to the power of x, it never had a negative y value. So you can't have it equal to negative 1. Therefore, you say undefined. Okay, you don't have to explain it. You can just say 2 to the power of x equals negative 1. If you write therefore undefined, that's sufficient. Okay, and then your answer is just x equals 4. There you go. But that's a typical exam question right there, what I just did. Okay, we good? 3 marks? Simple? Excellent. There you go. That's 5C. I've chosen the questions that if you want to practice more of that, question 4, 5C, more of that quadratic stuff. Otherwise, anything from 3 is good enough for you. You don't have to do 1 and 2 unless your index laws are poor. Go back and do that. Okay? But 3 and 4 from 5C, that should be enough for you to carry forward from chapter 5. Alright, now it's your own time. You got the whole session. You can do either the revision sheets, or you can do any of the exercises to catch up, or you can ask me questions. Trent.
差而已，不一样，还有